are going to start the lecture on advanced reaction engineering. So, in this course we will discuss about the trickle bed reactors, mass transfer correlations and one numerical problem or examples that will solve how to find out mass transfer coefficients and overall mass transfer coefficients that we can use for the design equation or the equations design equation that will develop. So, there we have to put that and then we can solve how to find out catalyst, weight, volume of the reactors and height of the reactors, since this is our trickle bed reactors. So, in this trickle bed reactors for a Diger conversions means conversion is fixed for a particular reactions. So, then how much catalyst you have to put, so what would be the volume of the reactors and what would be the height of the reactors. These are the design components we need. So, for that we will discuss. So, already in our previous class, so we considered A reactions, that is A plus B going to C. A is the hydrogen, that is the gas component, B is the organic component, that is the liquid, and C is the organic saturated compounds, that is the product. So, if we conduct inside of this particular reactors, so these are the parameters are givens that already we have discussed in your previous class, and we have to find out if we conduct these reactions here. So, gas, liquid and solid phase. So, in this particular trickle bed reactors we have to find out weight for a Diger conversion, that is the 55% conversions, and also we have to find out the percentage resistance developed for individual steps, means when reactant A transferring from bulk gas phase to the inside pore of the catalyst. So, what are the resistance are there and how what is the value of those numerical value of those resistance, individual resistance, and then total overall mass transfer coefficient or resistance we can find out, and then we can put that in the design equations, and then the design equations we can solve. Okay. So, here the additional parameters that is also given for these particular reaction systems that we have discussed in your previous class. Okay. So, bed porosity, pallet density, liquid density, that is given, viscosity of the liquids that is given, okay, and diffusivity of the hydrogen in the liquid, diffusivity organic product in organic liquids, that is also given, and then molecular weight of the component reactant that is given, and hydrogen solubility is given, and we are assuming that concentration of the B organic component that is not changing or concentration is constant, or that is once we can consider for this system. So, here this is our system. So, in the step 1 mole balance we have done. As per mole balance, this is the design equations for that packed bed reactors, dFA by dW, that is equals to Ra prime. So, in the rate law you know, means this is the rate law, this is minus Ra prime equals to kVg into CAg, okay, and then this kVg that is coming from here. This is the total resistance or mass transfer resistance, that is individual gas phase resistance this, and then gas to liquid interface to bulk liquid, that is the transfer of the component A, and this is bulk liquid to the catalyst surface, and this is inside of the pores internal diffusion reactions resistance if you know. So, then we can substitute here, then kVg value we can get, and we can substitute here, and then the design equations we can get in terms of conversions with catalyst weight. Okay. So, here already have discussed that step 3, that is the stoichiometry for isothermal conditions, concentrations in terms of these also we have discussed. Here pressure drop parameter is also given. So, that is equals to that amount, means minus 0.246 atm per meters, and alpha value we know, these correlations we discussed in our previous class also, and this is the final equation, that is the equation 4, the changes of the pressure inside of the reactors with changing of the weight of the catalyst, that is given. So, these correlations we can use, these correlations we can use, these equations we have to use, this equation we have to use, and then now we have to find out actually this kVg value by using different correlations. So, alternatively also means here you can see. So, dP by dL that is equals to minus beta 0, that is given. So, using these correlations dy by dW with changing of the catalyst, if you know this value alpha value by using beta in this correlations alpha value we can get, we can put it here. So, then equation should be simple in terms of x, y, okay, and w. So, here alternatively you can find out from here dp by dl equals to minus beta 0. If we integrate this, rearrange and integrate and then simplify, you will get these correlations, or you can say this. So, if you know alpha value, means using these correlations you can, beta 0 value actually is given. So, you can substitute here, other components you can find out, that is given, alpha value will get, that alpha value you can substitute here, then y equals to 1 minus w by 2 into alpha some numerical value you can put, and this you can use in the our equations here in the equation 3, okay, directly you can substitute there. Then the red equation or design equations would be simplified. Okay. So, here's after see here's combining all these 3 equations, equation 1, 2 and 3. The final equations we have discussed in your previous class 2, dx by dw, that is equals to kvg into 1 minus x by v naught 1 plus ex into y. So, this is the final equation, this equation you have to solve. So, here's kvg value we have to know before that, since E value we have to find out, V0 value we know for this particular ordinary differential equations if you want to solve. So, kvg value importance with this value. Okay. So, here's how to evaluate kvg value, that is the overall mass transfer coefficient for this particular system. Okay. So, here's if we want to get this kvg value, we have to use some correlations. Okay. So, here this is the kvg value, okay, this is the correlations. So, first we will find out H. Okay. So, how to find out H prime is given, solubility of hydrogen is given, that is H prime equals to 0.008 kilomole per meter cube per atm, okay, that is given. And from Henry's law, that is the solubility of the gas in liquids, that is given, that is this equations PAI that into H prime equals to CI, that is the interfacial concentration at the interface, gas liquid interface, that is the concentration of the component. If you know H prime is given. So, if you put it and partial pressures of component A if you put, then CI you can get. Okay. So, here's this equation, these concentrations and partial pressure, how they are related, CAIG equals to Pi by RT, this Pi we can substitute here. Okay. So, then these equations we can substitute here. Okay. So, then we will get CAIG we are substituting here. So, after substituting, these are the components, finally H and H prime how they are related. So, from this and this, if you substitute one by one, so then H and H prime how they are related with temperature and gas constant, from here you can get. Okay. So, here R value is this, temperatures at 400 Kelvin that reactions was conducted. So, that solubility also on that particular temperature we know H bar, H value, and then H prime value is given, H prime value we can put it here, then capital H that we are getting 3.8. So, in these equations here H value we can put, that is 3.8, numerical value we can put. Okay. So, next is the internal diffusion, H value we can find out. Next, internal diffusion value, this part we are finding out, eta 1 by eta k, that is the internal diffusion resistance and reactions. For internal diffusion and reactions inside of the catalyst force, what would be the resistance, 1 upon eta k value we want to find out, that is the internal diffusion. So, first we have to find out this H and then we are going to find out this value. Okay. So, this is the resistance equals to 1 by eta k. So, individual component eta and k we have to find out. Okay. So, it is the effectiveness factors and phi is the Thele modulus. So, how Thele modulus is related with the effectiveness factors, that we will study it in our UG course, also here also in our next class or some other class is there we will discuss more details about this type of correlations, how they are coming. Okay. So, here these are the correlations now we are going to adapt and we will use here, and in later we will discuss how that are coming. Okay. So, here if we know the Thele modulus phi, this is the R value of particle diameters, density of the particles, reaction rate constant, effective diffusivity. So, then thermodulus will come. Okay. So, for thermodulus R value that is given, see here the particle diameter is given, catalyst particles that we are considering or assuming it is spherical, its diameter is given, then its radius would be this, if we divided by 2, the diameter of the particles is given. So, radius is given. So, radius we can put it here, then reaction rate constant at 400 Kelvin is given. So, small k value we can substitute here, density of the particles, that is given, so that we can substitute here, and now effective diffusivity you have to find out. Effective diffusivity, D is the effective diffusivity diffusion in 4, means when component reach to the inside of the catalyst force, there would be a diffusion through that reactant component passing from one point to the another point. So, this is the effective diffusivity dl, that is the diffusivity in liquids, sigma value, that is the constriction factors that is given for this particular systems. Ep is the porosity of the catalyst particle porosity, that is 0.3 is given. Tau is the tortuosity factor, that is tau, that is equals to 1.5, that is given, and diffusivity of hydrogens in liquid, that is given. dl is the diffusivity of hydrogen in liquid, that is given. So, that component dl, sigma, Ep and tau, this value if you substitute here, then effective diffusivity you can find out. Effective diffusivity is coming, let us say this. So, this effective diffusivity we can substitute here, then we will get thermodulus. See, to find out the thermodulus phi, so R, K, rho p, d we have to substitute here, then we are getting 10. So, 10.8, that is the thermodulus for this particular system. So, thermodulus is 10.8. So, this type of correlations we phi and eta, these are the type of systems we can, this is for reaction, this is for diffusions, these are things, means this phi value when it is 10.8, here it is coming 10.8, very high value. So, when thermodulus is very high, then eta equals to 3 by phi. So, this correlation how it is coming we will discuss in more detail in later, but here we have to adapt this eta equals to 3 by phi. So, then eta value is coming, effectiveness factor is 0.277 for this particular systems when thermodulus is large value. 10.5 is very large value for this particular systems, therefore, effectiveness factor is very small value, and this eta value we can substitute here. Okay, how eta has come, and reaction rate constant that is given for this particular systems, then eta and k value if we substitute here, then the resistance for this particular point, internal diffusion and reactions, the resistance developed for the systems, that we can find out. Okay. So, H value we can find out, this value we can find out. Next, individual resistance we have to find out. Okay. Next, for the gas absorption resistance, this gas absorption resistance is this, here kg ai value you have to find out. See how, means this resistance equals to this 1 minus Eb and rho p h kg ai. Okay. Eb is the bed porosity that is given in the catalyst bed, the bed porosity 0.4 that is given, and particle density that is also given. The particles we are using as a catalyst for this trickle bed reactor, density of the particle is given, bed porosity is given. H value we have calculated at the beginning, H prime was given, H primes, from that H we have find out. Okay, that is calculated, that H value we can put. So, now to get this kgAi value we have to find out. Okay. So, kgAi value how we can find out, that is the absorption resistance transfer coefficient. Okay. So, kgAi, for that some correlations we have discussed in your previous class. So, these are the correlations kgAi how to find out for gas to gas interface. These are the correlations we have discussed in our previous class. Here Eg value we have to find out in terms of Ft feet pound force feet cube seconds. This Eg value we can find out from delta P by delta 8 multiplied with Ug. Ug value if we know, delta P by delta L value if you know, then Eg value we can get what are the form, that may be kilowatt per meter cube or maybe in that form. If it is kilowatt per meter cube, then we have to convert that into this. then that Eg value we can substitute here, then Kg Ai value we can find out. Okay. So, here for our systems this is the correlations. Okay. Kg Ai value we have to find out, that is the here's for our systems delta P by delta L, that is given 25 kilo Pascal per meter. So, pressure drops that is given delta P by delta L, that is 25 kilopascal per meter, that is given, that we can substitute here in these equations, and Ug value we can find out. Ug value how to find out? Ug, that is the Ug equals to volumetric flow rates, that is volumetric flow rates, and cross section area. If you know the cross section area, that you have to substitute volumetric flow rate, that is given. So, then this volumetric flow rate and cross section area of the systems if you know, then we can find out. So, how to find out cross section area? Cross section area equals to pi d square by 4, dp is the reactor diameter that is given, the reactor, that is reactor diameter is given, we can substitute here, then cross section area we can find out using this. Okay. And volumetric flow rate, how to find out? Molar flow rate of that component A is given at 20 atm 400 kelvins. F naught value is given at the problems. If you see there is given total flow rate 10 mole per second, and the reactions was conducted at 400 Kelvin, it is given in the problems. Okay. So, now molar flow rate is given. So, this at 20 atm 400 kelvins. Okay. So, we have to know, we know the molar flow rates of airs, that is molar volume is this at 1 atm 273 kelvins. Okay. This is mole per units was there, so we have to convert that in terms of meter cube per second. Okay. So, therefore, 10 mole per second, if we multiply with this and divided by this, then we will get this volumetric flow rate. So, molar flow rate was given, that we are converting into volumetric flow rates. Okay. Molar flow rate was given 10 mole per second at that particular temperature, we are converting that into volumetric flow rates. Okay. So, how to convert that volumetric flow rate is given. Okay. So, 10 is substituting here, molar volume is given, and then 1 atm 20 atm 400 Kelvin 273 kelvins, that way multiply and substitute division we have to do, then volumetric flow rate we can get, that we can substitute here, cross section area we can substitute, then Ug, that gas velocity we can find out Ug value, that Ug value we can substitute here, and delta P by delta L is given. So, then Eg value we can find out. So, Eg value we can substitute here, then Kg Ai value we can find out. Okay. So, here okay, so Eg value if we know or we can find out, that we can substitute here. So, Kg Ai value find out. So, once you know all components, then Rg value, gas absorption resistance we can find out. Okay. For our system, see here Kg Ai value we have find out. So, here Eg value is coming from here, Eg value delta P by delta L into Ug. So, here delta P by delta L is this and Ug value is this. So, then it is coming kilopascal per second, we are converting that into pound force feet cube per second. So, this kilopascal seconds we are converting into this. Okay. So, it is coming 10.9 Eg value. This Eg value we can substitute here in these correlations, then it is coming 6.47 second inverse. So, Kg Ai value we are substituting here, H value is given, bed porosity is given, density of the catalyst particle is given, then resistance is Rg, that is the gas absorption resistance, this resistance we are finding out, that is 36.5 kg second per meter cube. Okay. So, Rg value we find out using that correlations. Okay. Now, in the this part is done, this part is done, this part is done. Now, KL Ai value we have to find out. Okay. This resistance gas to liquid interface, bulk liquid interface, where component A is transferring or mass transfer is there. So, that part we want to evaluate, gas liquid interface to bulk liquid transfer of component A, that is the resistance RL equals to this you can see 1 minus EB rho P by KL Ai. Here rho P is given, particle density, bed porosity is given, So, only KLAI you have to find out. For that you have to use correlation. These correlations we have discussed in your previous class. Our system is organic, therefore, we are taking this, not this. This is for aqueous, this correlation is for aqueous medium, but in our case organic second component B was the organics. Therefore, these correlations we have to use. Here Galileo numbers and Reynolds number, Smith number we have to find out, and DL also diffusivity L that is given. So, what is Galileo number? Galileo number is this, Smith number is this, and Reynolds number for this particular system is this. So, these are the components you have to find out by considering liquid viscosity, diameter of the particles, superficial mass velocity of liquid, diameter of the particles, everything are givens, the data are givens, G value is also given. So, all these components we can find out. See here G is the givens 5 kg per meter square second, superficial mass velocity for liquid, diameter of the particles is given, viscosity of the liquid is given, density of liquid is given, G value is given, diffusivity of hydrogen in liquid is also given. Then all these components we can substitute in these equations here. So, for Reynolds number we have to find out, for G value is given, dP value is given, viscosity of the liquid is given. So, Reynolds number will come, Reynolds number is getting 5.55. See, Reynolds number is getting, we are getting 5.55. Okay, let us say the Reynolds number that we are getting 5.5, that is the liquid Reynolds number is this, and Galileo numbers that also we are finding out. dP we know, density of the liquid is known, dP is known, density of liquid known, G value is known, viscosity of liquid is known. So, if you substitute, Galileo number is coming this. Smith number similarly we can find out, mu L is given, density of the liquid is given, D1 that is the diffusivity hydrogen liquid is given, that Smith number is getting this. So, Smith number, Galileo number, Reynolds number, if you substitute in these equations, Reynolds number, Smith number, Galileo number, so then and GL also, then KLAI we can find out using these correlations. So, after substituting this, the correlations KLAI, that is the constant KLAI mass transfer coefficient, that we are getting this. Okay. So, this we can substitute here in these equations, other components are given. So, then the resistance for this particular interface to the bulk liquid transfer of mass we can find out this. So, RL part we can find out. So, KLAI part we have find out, and that we are substituting here or here also, rho B is given, rho P is given. Okay. So, KLAI value is known, then RL resistance we can find out. So, next part is this bulk liquid to the catalyst surface, Kc AC value we have to find out. So, for Kc and AC value, so this is the resistance for bulk liquid to the catalyst surface. So, here Kc AC value how we can find out, here I said Reynolds number that was 5.55 we have find out. So, once it is 5.55, there is some correlations I said 5.55 means less than 20. Okay. So, once that Reynolds number is 5.55 that was given, so then these correlations we have to use, mass transfer coefficients. Here Reynolds numbers we have find out, Smith number we have find out, Sherwood numbers that is the Kc, dP, alpha and dl. So, here dP that is the diameter of the particles that is given, and alpha value Kc AC value means Kc value first we have to find out. So, here see AC equals to 6 by rho P dP, diameter of the particles, density of the particle is given, density of the particle is given, diameter of the particle is given. So, if we put here interfacial area per mass of the pellets, that is AC we can find out, AC is required here, this value is required here, and then Kc value from Sherwood number or these correlations we can find out. Sherwood number equals to 18.4, Reynolds number and Smith number that we have find out in our earlier calculations, Smith number 893 and Reynolds number 5.55 that was we have measured, that both we can substitute here, then it is coming Sherwood SH prime that is 18.4. So, Sherwood number equals to Kc dP by alpha. So, we have to find out Kc, Sherwood number equals to 18.4, dl, that is the diffusivity, that part is given, and dp, that is given. So, then Kc value is this. So, we know Ac value is this, Kc value is this, then Ac and Kc both we can substitute here. Okay. Then Ac and Kc value if we substitute here, see, then the resistance due to the bulk liquid to the catalyst surface, the component A transferring, the resistance we can find out easily. Okay. So, individual resistance we have find out. So, now see the total step 8, that is the total resistance and percent resistance that you have to calculate. So, these are our kVg value, that how we can find out individual resistance we have find out, and then we sum up, then this RT equals to gas, liquids, and then liquid to the bulk liquid to the catalyst surface, and this is inside. So, these are the value we have find out. If we sum up, this is the total resistance. Okay. So, then individual resistance we can find out for gas absorptions, gas in the bulk or sphericals, this is liquid, this is gas, and this is solid. So, gas component A transferring from here to there, catalyst pore. So, here the resistance, that is percentage is 36.5 divided by total multiplied with 100, then 0.01 percentage. Gas interface to the bulk, gas interface to the bulk liquid, the resistance, that is 4.15 into 10 to the power 5 divided by totals multiplied with 100, then 74.37 percentage for this point resistance bulk liquids. So, bulk liquid to the catalyst surface, so 0.23 divided by this total. So, then we are getting this equals to 4.12 from bulk liquid to the catalyst surface, the resistance, that is 4.12 percentage, and interfacial diffusion and reactions, that is 1.2 divided by total. So, then we are getting 21.5. So, from here to catalyst surface pore is there. So, here the resistance reactant A diffusing inside of the pore, the resistance is 21.5%. So, from these examples we know how to find out individual resistance, and then if we sum up, then overall resistance we can find out. Okay. So, and here this is the kVg value, how to find out. kVg is the overall transfer coefficient, that is 1 by h this, and this bottom part is the total resistance, that is the RT, that RT we have find out. So, then we can find out kVg value. Okay. So, this kVg value is useful here in these equations. In this equation this value we know, kVg value now we find out. Now, this equation 5 we can easily solve to get x versus w. Okay. See, this is the kVg value we find out, V0 value we know, epsilon value we know, y value if it is given it is very good, if it is not given we can find out. So, here see. So, now these equations we have to solve. This equation 5 we have to solve. So, this is ordinary differential equations. By using ordinary differential equation solver we can solve this. So, here's E value we can substitute all component except x and y. Here see beta 0 value is given, we can substitute here, AC value is given, PC value, that particle the catalyst particles, that is the density, that is given, and EV bed porosity is given, total pressure is given. Okay. So, if it is known, then alpha value we can know, alpha value it is find out, we can substitute here. So, then y value we can find out, and y we can substitute here. So, y we can substitute here in terms of known quantity, means alpha value is known. So, 1 minus w and some numerical value would be there, that we can substitute here. So, these differential equations we can solve by using ordinary differential equation solver for say let us say 60% conversions if you want to get. So, then that amount of the weight of the W we can find out, let us say x equal to 60% conversions if you know want for this particular reactions. So, then how much amount of the catalyst that is required. After solving this we can get that much amount of the catalyst is required, that we have to put inside of the reactors to get, this is the Diger conversions. Okay. So, if you know the catalyst, want to know the catalyst weight is required. Now, reactor volume reactor volumes catalyst weight divided by density of the bed. So, that we can know, that is quantity of the catalyst is required, density of the particles we know, bed porosity we know. So, then that would be, after substituting all these components, the total volume of the reactors that we can find out for x equal to 60% conversions, that much volume of the reactors you have to take and that much quantity of the catalyst you have to record. And if you want to know the height of the reactors, so what would be the height of the reactors, this height. So, that also we can find out if we know the volume, if we divide it by the cross sections area based on this. So, based on the diameters that we have evaluated before. So, we can substitute here, then 48.83 meter, that would be the length or height of the reactors. So, volume of the reactors we know, height of the reactors we know, and how much quantity of the catalyst you have to place inside of the reactors to get this percentage of conversion, that you know. Okay. So, this is the way we can design these trickle bed reactors to find individual components. This is very lengthy calculations, but we should know. Okay. So, how to deal with that or this type of trickle bed reactor problems. Okay. So, now also we can find out the consumptions or component A or component B and how much component leaving from the reactors also. So, moles of A or hydrogen that is converted, if you know Fa naught into x, then we can substitute here. Okay. Okay. So, here it would be 55%, let us say what happened, we have to put by mistakes there, it would be for this particular system it was 55%, not 60%. Okay. So, based on that you have to do the calculations. Okay. So, not 0.55. So, now if the molar flow rate is given, mole fraction is given, total flow rate is given, conversions is 55%. So, then 2.75 mole per second, that is reactant A consuming or converted inside of the reactor for this particular reactions. Moles of organic leaving, how many moles means total, that is the mass velocity of for organic component into cross sections area, if we multiply, this is the mass velocity of that organic liquids, that was the reactant B, and multiplied with the cross sections area, then mass rate we can find out divided by molecular weight or moles. So, then we can find out this for component A, subtract the moles of the hydrogen that is being consumed, that was this 2.75, means totals the mass that is consuming for this reactions. With that, if we number of moles of hydrogen that is being consumed for the reactions, if we subtract, then that amount of the moles of organic component that is leaving for that particular reactions that we can find out. Okay. So, component A and B means component B, that is the consumed and leaving from the reactors, that we also can find out. Okay. So, thank you. Means today we have deal with the trickle bed reactor problem. So, the problems is very lengthy, but we should know learn each and every step. So, how to deal with this type of reactors and this type of the problems is there, so what are the parameters are required. Okay. So, these are the very importance. Okay. So, we should know means individual step by step calculations, means basic things just I am writing. So, here see just summarizing this is the design equations, this is the rate equations, and this is the mass transfer coefficient, total overall mass transfer, these individual resistance you have to find out, then it we can substitute here, and from the stoichiometric correlations, this type of correlations we know. Here for y, this type of correlations is known, we can substitute here, or either differential equations we can solve, either way. So, here this is the equation, final equations we are getting by combining all these equations. This equation basically we are solving, and these equations KVG value we are evaluating by using this individual mass transfer coefficient, then overall mass transfer coefficient we are finding out, that part we are substituting here, and these differential equations we are solving. Here V0 E is known, alpha y according to this pressure drop or this type of equations is available, or depending upon that if we solve this, then conversions and weight of the catalysts, by that way how much amount of the catalyst is required, everything we can find out here step by step. So, individual resistance how we have find out, so that is basically you have discussed. Okay, individual resistance we have find out, and then we sum up, and then total resistance we find out. This is the total resistance, then KVs easily come out and we can solve the equations. Okay. So, today is up to this. Thank you.